Welcome and thanks for joining us. My guest today is Ronald Ross, Ron, a fellow at the National Institute of Standards and Technology. Ron, always good to have you with us.
It's great to be with you too, Tom.
I think we can call you the dean of cybersecurity federal experts here after all these years. And I want to start, though, with something that's new for you and something you're continuing to work on, and that is this whole notion, and there's a special publication for that, you might say, of engineering trustworthy, secure systems engineering. I think is the key word here. And of course, the publication is 800-160. What's the basic concept? And give us an update.
Well, this publication is extremely important, and it's not that well known when you look at all the other publications that NIST has had over the years, from the crypto work that we've done, the NIST risk management framework, the cybersecurity framework, and all of the previous work that was under the framework umbrella with all the controls and the compliance things that go with that. Largely, that work was done focused on enterprise IT systems. That was really where we started a couple of decades ago. Since that time, there's been a massive innovation revolution. You've seen it. We've all lived through it. There's been a massive convergence of cyber and physical systems. So we have the framework tool still there, but now we have to start looking under the hood a little bit. We have to get down to the place where industry is building the hardware, the software, the firmware to see what kind of components are being built, how do they work together when you bring those into a systems context. And an engineering process is very different than a framework-based process. You start with the stakeholders who really tell you what's the mission of the organization, what's our business model, what are we trying to achieve, and then the engineers go out and build a system that can help carry out those organizational missions and business processes. And as they do that, they have the distinct privilege of looking at developing their security requirements from the top down that are specialized to that mission of the business operation. And they also have to make some trade space decisions. How much security is enough? What kinds of things do we have to worry about with the new threats that are out there today that we didn't see several years ago? So it's a completely different way of looking at the problem from the top down, as opposed to a framework where you start with a set of controls, you tailor, and you work from that perspective.
And you mentioned the cyber and physical systems. And I guess that is underscoring the idea that every physical system now is entirely under electronic control for the most part. And that's true in the military and civilian domains.
Yeah, Tom, this whole space has changed so dramatically over the past even 10 years. This convergence of cyber and physical systems, even looking at your automobile with the hundreds of computers that control your entertainment system, but they're also controlling your critical safety systems like your brakes. And the common denominator in all of this, whether it's an IT system or OT or IoT device, a smartphone or a tablet, the nerve center is the computer driven by software and firmware. And a lot of it is not as trustworthy as it needs to be. That's really where engineering kind of goes beyond what the frameworks can do. It can get under the hood and look at those key issues that you just don't have quite the transparency. I talk about the black box a lot. That's kind of the stack of hardware, software, middleware, operating systems, applications, and all of that works together in an environment, and then we connect everything together. We have very little visibility and transparency into that black box. And so what's different about today, and I think we've greatly underestimated the impact this is going to have. If we're talking 20 years ago and you're talking about the blue screen of death and your computer goes down, it might be an inconvenience. But in the world of complex systems today, cyber physical convergence, computers are being pushed into everything from pacemakers to power plants. And every time that computer is part of that cyber physical system, there's potential for bad things to happen that we never anticipated before. So it's a whole new world we're going into. And unfortunately, I don't think we're quite as prepared as we need to be. And that's why we're really focusing on the engineering aspects and the notion of assurance and trustworthiness, which, it isn't as simple as having secure by design. You do it one time and you're done. These are complicated problems. These products come out and each one of them may have a different degree of trustworthiness. So how much do I know about the products I'm using in these critical systems spread out through the entire critical infrastructure, the water distribution systems, the power plants, manufacturing plants? How much do I know about the technology? Who built it? How was it built? what processes, how much should I trust it? Because I may have to use products that don't have the highest degree of trustworthiness, but I need to go in with my eyes wide open so I can do risk mitigation. And that's the part that the engineers have a leg up. They can really get under the hood and see things that a lot of people can't see in a framework-based environment.
Right. And I guess maybe another quality that these types of systems have is that they're not static. They're updated, they're changing, and with artificial intelligence, their characteristics could change in an automated fashion, such that the architecture and maybe even the engineering relationships are very different a year after they've been on the road, so to speak, than when they were first issued.
It's very true. Everything in the world of computers is dynamic today. Everything is changing. And this is why one of the things that the engineering document that we produced in this, we actually have two volumes, one and two. And we're proposing a different strategy in these documents as well. Traditionally, for the past 40 years, our strategy has been penetration resistance. Stop the bad guys at the front door, keep them out of the system. Well, we know even with everything we do on our best day, with the best controls and the best processes, whether you're using ISO, the NIST cybersecurity framework, or the risk management framework, you may be able to stop 80 to 90% of those attacks. But the very sophisticated adversaries, the advanced persistent threat, the folks who are well resourced and have the knowledge, skills, and the abilities, they know our system is better than we do. So what do you do when those initial safeguards, the protection measures fail? And now the adversary has come through the front door, they're in the house. This is where we have a multi-dimensional protection strategy. You do everything you can to keep them out. Once they're inside, you try to limit the damage they can do. We have lots of technologies that can help us do that. And the ultimate goal is to make these systems resilient so they can withstand that initial attack, maybe even absorb it. Even if the adversary is in the system, you've architected and designed the system so it's not a one and done. It's not a knockout punch. And we have a lot of technical debt out there from decades and decades of systems, a lot of legacy stuff out there. Sometimes it's very hard to retrofit some of these things that we're talking about. So we need to have that new approach. First of all, it's kind of a strategy. It's a vision for the future. And then our great industry partners, they'll figure out a way to do it. They're already doing a lot of this stuff, but it needs to come together in more of a focused effort.
Yeah, many years ago, people talked about the idea of self-healing networks. And I don't think they quite meant it as extensively as now, but that kind of concept maybe lives on in this new era.
Yeah, I think that's a really good. There's been a lot of work done. I think DARPA might have done some of that work looking at the human body. How does the human body absorb, viruses and bacteria? We have a whole ecosystem within our human bodies that allow us to do a lot of things to fight off these diseases and things like that. Although sometimes, you can get unlucky if you have cancer or something, and those things are devastating. So it's not a perfect system, but resilience is about being as good as you need to be to keep the mission alive. And even if you have to operate in a degraded or debilitated state, as long as you can continue to support the mission, that's really what the focus is on the engineering side of the house.
And in building systems like this and calling for engineering trustworthiness and resiliency and security into them, just as a basic question, it's coding, but what's the difference between coding a system and engineering it?
Well, secure coding is certainly important. That's the way you develop software. But in a system is composed of many, many hundreds and thousands of different components. There are software components, there are hardware components. It all comes together in the engineering process. So it's not only focusing on secure coding techniques, although that's a very important part of the solution. The types of programming languages that you use, some programming languages are much better at building software that's more trustworthy. You're trying to wring out all of those weaknesses and deficiencies in the code. But the sad truth is that we're dealing with trillions of lines of code, billions of devices, and ubiquitous connectivity. That's the way the world has been built. So complexity is our number one threat, and we have to be able to reduce and manage that complexity. Otherwise, it's going to bury us. And so the secure coding techniques are a way to simplify the software, use better programming languages that can eliminate some of those kind of core vulnerabilities that come or weaknesses that come from a typical, programming process. Artificial intelligence and some of the machine learning, I think that's going to help us build better software over time. But there's always the human component. The software components can be really good, but you always have to bring a lot of those components together in the systems context. And you're never going to have perfect software. You're never going to have perfect anything. And so it becomes an engineering task to figure out, how much do I trust this component? What does this component interact with? And how do I make sure that I can have the highest level of assurance? Where assurance is, how much do I trust the component? And bringing all the components together into a capability. How much can I trust that it's going to do what it's supposed to do and not fail at inopportune times? And so, when you're talking about critical infrastructure like the power plants, we've seen what happens when you lose power during a hurricane. We've experienced that in Florida over the last several months. But what happens if there's a coordinated attack? Some of this malicious code that we're worried about, where the adversary, we talked about coming through those initial defenses, putting their malicious code within the system and not triggering it now, but waiting until the opportune time in maybe a coordinated attack. We have to be able to spend the effort to make sure these critical systems are locked down as much as they need to be. And that's going to take some effort. It's not always going to be the cheapest solution, but when you're talking about the lights going out for months, when you're talking about developing weapon systems for our warfighters on the battlefield, they have to be successful. They defend the country. There's so many things in the critical infrastructure. We'll talk maybe a little bit about the space systems, a little bit later, but there's a ton of stuff in the critical infrastructure that needs our attention. And this is going to be a partnership, just like everything we do in this country, where we're trying to solve difficult and challenging problems, from putting the first man on the moon 50, 60 years ago. This is the problem for the 21st century, and it's going to be a government, industry, and academic community unified effort to get these things solved.
And even within an organization, it sounds like it requires not just the integration from an engineering standpoint, but from a functional human standpoint, because the many components that come together often have different owners, and they might even be related to different programs within the agency, let's say. So somehow people have to come together to enable that kind of engineering, I would think. Fair to say?
It's a very good point. There's a couple issues there. One, our organizations in the federal government, for better or for worse, the Chief Information Security Officer has all the cybersecurity responsibilities, and that individual works for the CIO. That's a staff officer. Yet you have in many federal agencies that are building systems, whether it's NASA, the Department of Energy, or the DoD building weapon systems, they have mission owners who are building real systems out there. They also have to worry about cybersecurity. So one of the things that's hurt us over the last couple of decades is that cybersecurity has been its own stovepipe. The fact that it's hardwired into the CIO's office, it becomes our entire focal point. And I'm talking about someone who has spent a career doing cybersecurity. But what we miss is when you have that stovepipe, the engineering world, they're not only worried about security, they're worried about safety, they're worried about resilience, survivability, reliability, all of those things that are in an engineering process. NASA is a great example. Safety is an emergent property of a system. They have an engineered system that produces a spacecraft, and that spacecraft has to operate in hostile space, not just hostile cyberspace, but hostile physical space. So safety is an emergent property that comes out of a disciplined engineering process. It turns out that security is also an emergent property. That's why you can't bolt stuff on at the end of the life cycle. There's some things that you just can't secure in a system after the fact. That security has to be engineered in from day one, across from the first time the stakeholders get involved with the bright idea, all the way through the system requirements development to the architecture, the design, the integration, all the way through operations and sustainment. And you do have a people issue too. The other issue on that front is that what we found with the NASA project is we have system engineers who are building stuff, and then we have a cybersecurity professional community who've been doing the frameworks and all the protection on the enterprise side. And now you're trying to bring those people into the engineering community. They speak different languages. They have different processes. So one of the things we're trying to do is examine the people part of that component because we have really smart people. It's just they've grown up in different worlds. We don't have the luxury anymore of stovepiping cybersecurity. It has to be brought into the larger organizational processes, which includes engineering. Because the only way, it's kind of like I use the example of NASA, the integrated project team. If you remember back years ago, when NASA was going to launch the Apollo program and the shuttle program, you'd see a bunch of people around the table, the mission control. Each one of those individuals around the table, they would go through the countdown phase and they would go to each individual, give them a thumbs up or a thumbs down. If you got a thumbs down, they stop the launch sequence and they fix the problem. That's the best example I can think of an integrated project team. And that's what we're trying to build on the security side. So security people they're not going to be the most important group in the room anymore. They're going to be part of a team where you have many, many different considerations in the trade space that's going to help that system be developed so it's correctly developed and it also is fit for purpose. It can put steel on target, so to speak. So that's the difference.
You've been discussing something we should get into specifically, and you mentioned NASA and use that example. There is a project between NIST and the Jet Propulsion Laboratory on this whole matter. Tell us about that project, what's going on, and what are the expected outcomes?
This is the best project I've worked on in my not just my 27 years at NIST, but in my entire cybersecurity career. It came late in my career, and it happened. This was kind of an outgrowth of the 80160 project. We published that engineering guidance back in 2016. It's hard to believe it's been 8 years. Had a conversation with some folks at Jet Propulsion Laboratory one day and NASA. They were working on a project, and they were expressing to me their frustration. I've heard this across almost every federal agency who builds things and who are using our risk management framework or our cybersecurity framework. They say, we got engineers out there. They're trying to build stuff. And they're frustrated because they can't apply the framework, which is largely a compliance-based exercise, to the engineering process. It's not that the framework is incorrect. It does really well for what it was intended to do, but it can't always solve the engineering problems when it comes to security. So we started having a discussion 2 years ago. We went through all of the issues. And then finally, NASA, the mission director, and the Jet Propulsion Laboratory, who's their FFRDC with Caltech, supporting them very closely, they offered up a real system for this experiment. How do you apply the concepts in 80160, the security design principles, which come out of a principled engineering process, to a real system? And this happens to be a spacecraft. And so the spacecraft is called the Sunrise Satellite System. It's a kind of an array of 6 CubeSats, and they're all launched and they all work together. They're taking some readings from the sun, some radiation readings and all that, and they're trying to see how these particles affect spacecraft and people. And so they built the system. They started in the life cycle stage, the phase A, which is the concept, and they go all the way to phase D, which now the Sunrise system is done. It's waiting for a ride into space. So now we come along and say, okay, we have a problem. Let's try to do a simulation of that same development process. All the artifacts they used to develop that Sunrise space platform have been done. They have a ground data system, which is the way you communicate with spacecraft. And so now they're going to try to repeat through a simulation. They're going back and repeating the entire development process for a subsystem of that Sunrise satellite system. They were focusing on the ground data system. And they're going through the whole process again in a simulated mode. And they're saying, if we were to do this again and use the security design principles from 80160, what things would have changed? What kind of vulnerabilities are there that we found at the end of the first process that we could fix going through again? And so we're learning a lot of things here. We're learning how the content in 80160 can be applied to a real system in a real life cycle. It's going to impact the kinds of changes that may emerge in the next generation of systems, because this is an experiment. It has hypotheses. It has outcomes, objectives. It's a classic NASA experiment, taking the NIST content and applying it to a real system. Everything we're learning about this, we're going to document and we hope to publish. So all of our customers, anybody who's building systems, there's going to be a way to generalize what we learned from this project. And in the world of these sophisticated threat actors, in other words, space travel today and space is the next frontier. The DoD, the weapon systems, the communication systems, it's got a lot of important stuff going on. It brings together the commercial marketplace for space and also the military side of the house. And so the kinds of threats that we're seeing today, where the adversary gets through that initial line of defense and now they're inside the system and they're looking at where you're deploying your safeguards and countermeasures. So it's not good enough anymore in a compliance-based framework to say, hey, you've got to have two-factor authentication or access control or encryption. Where you put those safeguards, the engineers have a much better view inside the black box. And they can tell you that sometimes where you're putting those safeguards is not the best place to actually do the job. And so this is an exciting project. We're going to learn a lot of things. Sometimes there's going to be failures, there's going to be great successes, but the ultimate objective is to better protect our cyber physical systems in a very hostile threat environment. And I think we've kind of greatly underestimated. We've been focused on innovation and building all this technology. Now we're having to take a step back and say, okay, how vulnerable is this stuff that we're building? Where are we using this? And what could happen if there's a catastrophic failure? How do we recover? How do we become resilient? So this is why I'm so excited about this project. And this experiment is not going to stop with one and done. NASA's already looking at expanding the project after it's over. We're working with other partners across the federal government who have similar problems, whether it's the DoD or the DOE or anybody that's building systems. Even the private sector is looking very closely at this because we have a lot of great partners in industry who are running their own engineering processes. And so, there's a lot to be learned here. And we, as scientists and engineers, we can't rest on what we built in the past. We always have to look forward and see what we've done, how we can improve upon it. And that's really why this project is so important.
Yeah, and we have seen real examples of where systems have had functionality or capabilities designed in them that are only known to a few and have caused, rather than their intended purpose, say of safety or security, have had the opposite effect out in the real world when users get their hands on them, which kind of gets to the heart of the idea of everybody understands what's going on and the team approach to development here in engineering.
That's a very good point because we tend to be hyper focused on cyber attacks and the adversaries. But when you look at one of our publications on risk assessments, there's really four different types of things that are threats to systems. One is obviously the hostile cyber attacks, but you also have errors of omission and commission where good guys do bad things either on purpose or sometimes inadvertently. And they'll push out, a software patch that'll go worldwide to 100,000 customers. And next thing the airports are going down. So, this is the world that we've built. It's very powerful computing technology and ubiquitous connectivity. And when you have that kind of capability, you really have to double down on assurance to make sure that whatever you're doing, you understand what the effects are even ahead of time. And so double checking, we have a lot of there's a requirement in the new publication we're releasing for the CUI project. It's called dual authorization. And that means basically you have two people who are in the decision-making process. It's like the two Air Force captains that sit in those missile silos. They both have keys, and they both have to agree before those missiles are launched from the National Command Center. So these are the types of things that we didn't think about a long time ago, but the fact that you have this power and the connectivity has brought this right into the center stage. And it's really pretty serious stuff.
And just to get back to the Sunrise satellite system, then what you're looking at is a way of knowing that when this is launched, that it can respond and overcome various difficulties that you are testing against.
Exactly. And so, for example, when a satellite or any spacecraft is launched, you have the ground data system that's communicating with that satellite. It's taking data coming up and down the link. It may be pushing software patches up or fixes, software firmware fixes. So just think about the effect if an adversary takes control of the ground data system and they can corrupt those software updates, they could potentially bring down that satellite. And that could be a military application. This is it's kind of a common problem, and that's why it gives me great hope that we have the tools, the techniques, the processes that we understand. We just have to apply them in a disciplined and structured approach.
And getting back to 800 160, where we started, that has been a couple of years since revision. What are your plans for it? Because it sounds like you're learning more about this idea of, engineering trustworthy, resilience, security into systems all the time.
The biggest problem with even a good publication is that it can sit on the shelf and people can look at it, they can walk around, they can open up the pages, they can admire the content inside. But the question they always come back is, how do I actually do this? And so the plans for 800 160 Volume 1 is to take a series of these experiments now and answer that question. How does a system engineer working with an integrated project team of maybe security professionals, all of the integrated team members that are going to be there to help them build a system that can do what it's supposed to do and not do things it's not supposed to do? That is what could generate a series of NIST publications on implementation of 800 160. How do you actually do the first three phases of the system development lifecycle, where you have stakeholder engagement, you've got mission business analysis, system requirements. How do you look at the architecture definition, the design? How does the integration come together in a real world situation? And so this has the potential for an enormous body of knowledge to come out of this that can be generalized and shared across every federal agency out to the private sector. And again, we can learn from all different parts of this problem space. You have the private sector does engineering. We'll learn from some of the things they're doing. They're going to learn from some of the things we're doing. The ultimate objective is to get a set of guidance out there that our customers can use to build, operate, and maintain more secure systems in this new world of cyber physical convergence and massive complexity and attack surface.
And since you are Ron Ross, I feel like we can't have a conversation without going back to the basics. And we did talk briefly about 800 53, that special publication. And that is never a static thing either, is it? The basic controls for all of this.
That's where it all started 20 years ago with the FISMA legislation. And it was a great project. I loved doing that work on the FISMA team for years and years and years. I moved away from that work in 2020, and my successor is a fantastic computer scientist and engineer herself, Vicky Pillateri. And she's going to put her own stamp on this project. Her real contribution here is keeping that catalog of security and privacy controls up to date. And one of her focus areas is how do we deliver that content to our customers? And that's going to be the huge change that a lot of you are going to see out there. You know about the 853 and the 53 alpha and of the FIPS 100, the FIPS 199, FIPS 200. Those are all static publications. They're paper-based publications, and they get delivered in PDFs now. What you're going to see now is that content has all been transformed to the website. It's on a website called CPRT. It's an online catalog of all of our security and privacy controls, and this is going to be the way most of our content, even the 171, the CUI work, is all going up to the website. So you come up on the site, you can pick any control. You can see what the control says. You can get the guidance about the discussion. What does the control mean? How do you implement it? And all of our assessment procedures, all of that stuff's going to be interactive. That's the first thing that the customers are going to see. The bigger part of that is keeping the content up to date in near real time. We don't have the luxury of taking 5 years to update, the 853 in a paper-based document or even a PDF. If there's a new threat that emerges, and we've had this happen several times already, the intel community, the DoD, private sector would say, here's a new threat. You guys don't seem to have a control that can counter that threat. Here's what we think you ought to do. Or they come to us and say, what do you think we ought to do? We develop the control. We put it out on the website for a beta test. You can see it right there. We can move very quickly. We get public comments back on that. We update it. We massage it. We lock it down, and then it becomes part of that interim update. So instead of revision 5 in 853 waiting 5 years, revision 6 may be a 5-year wait, but in the interim, you're going to see lots of smaller changes that are going to support our customers' needs day to day. That's a powerful new concept. It kind of goes a little bit against the typical standards way we do business because standards is sometimes very slow. It's very coordinated for lots of good reasons. But sometimes you have to have processes that are up for the moment, what you're seeing today, and the threat space is changing faster than we would like to see, and we have to have the ability to respond to that. So that's what Vicky and her FISMA team are going to be up to, and I'm really excited about that aspect as well.
Yeah, you might say you're really building resilience into the NIST process for keeping up to date.
Absolutely, absolutely, well said.
And will 160 be undergoing a revision or in the same manner, or will that be the more classical revision?
It'll be more classical. I think 160 Volume 1, we always are in the update mode in some sense. In other words, once that publication, it was updated, I believe, in 2022. That had a complete revision from the 2016 version. And there are some things we'd still like to do. This business never stands still. Even if you do your best work in 2022, 2 years later, we're interacting with NCOSI, the engineering organization. We're interacting with the private sector engineering, efforts. We're learning the NASA project. We always want to push the envelope a little further. So I would imagine that document is going to be updated in the next year or so. The 160 Volume 2 is an excellent publication if you have legacy systems, which represent 90% of the installed base out there today. This gives you cyber resiliency goals, objectives, techniques, and implementation approaches, which can really help that, focus on that legacy system right now. You go to war with the army that you have, not the army that you want. So what do you do with the legacy system? We can provide some near-term help before you have to go back and re-engineer because you're not going to rip and replace. Most of this stuff, the budgets are tight. We got to do what we have to do to limp along. And so Volume 2 is a great publication to help you make that legacy system, your installed base, more cyber resilient.
And just a final question for those CISOs and those CIOs and those agency mission owners out there. This is a lot to take in, and the threat environment is many and varied, especially as we extend it from just this pure cyber domain to the cyber physical domain. What's your best advice for the next year or so for people to make sure that they actually have resilience and security, even as they work at compliance with the rules and regulations?
First of all, I take my hat off to everybody out there. You talk to the CIOs, the CISOs, the mission owners, the systems security engineers, the cybersecurity professionals. These are the folks that get up every day and do the heavy lifting. And well, I'll tell you, they do a tremendous job. It is a very difficult and challenging set of problems. The work is relentless. Sometimes it's very frustrating, it's tiring, and they soldier on every day. My best advice, whenever you have a difficult and challenging problem, don't become overwhelmed by the enormity of the problem. Break it down into meaningful chunks. Do one good thing every day, lock it down. Start that solid foundation. I like to focus on the architecture, understanding what's in your environment, what your system looks like, the hardware, the software, the components, because one of the things that's central in all these discussions today is reducing and managing complexity. So getting rid of a lot of the clutter is job number one because you can't hope to lock down a system if you're overwhelmed by the number of things that you have to deal with. It's physically impossible, even with the best tools that we have. So focus on the architecture. There's a lot of great programs out there that can give some very near-term relief. The Zero Trust Architecture Initiative, the CISA, Secure by Design. There's a lot of things you can do to reduce and manage that complexity, least functionality, get rid of the ports, the protocol services that you don't need. And there's a lot of things that don't require a huge investment in time and energy. They're kind of the simple spring house cleaning. And then once you've got that done, you can clear the air a little bit. You can focus on those things that are the highest priority, your high value assets, your critical systems. And that's where the focus ought to be. Take some time to understand what assurance is and why trustworthy systems is not about, total security, either all or nothing. It's all a graded level of trustworthiness because you've got many different commercial products out there. You got to make some tough trade space decisions. you're working with cost, schedule, and performance. That's the way the reality of this world is. And, those are the kinds of things that you have to work with every day. And so again, we're going to get there. It's going to take a while.
Right, but make your bed first thing when you get up.
That's what I do.
All right. I want to thank you for being with us. Ron Ross is a fellow at the National Institute of Standards and Technology. As always, great speaking with you.
Thanks, Tom.
I'm Federal Drive host Tom Temin. You're watching Federal News Network. Let's go back to the studio now for more on the Risk and Compliance Exchange.